I wanted to record a really brief walkthrough of the integration here because you're going to have to do this on the homework assignment, and I thought every little bit helps. Again, I think you'll find that the integration is pretty straightforward. Really, the hard part is just setting it up, which is what we had done just before class ended. So I'm actually going to erase all of this and sort of redo it. So give me one second. I see we have a student asking a question. Hopefully what we do here clears this up a bit. Okay, let me scroll down a bit. Okay, so like I said in class, we're going to evaluate this as the sum of integrals along the beam. Because ultimately what we're trying to do is sum the energy across the entire beam. What I'm going to do is I'm going to integrate, so let me integrate from 0 to 10, the first one, and then integrate the second set from 10 to 30. Now, and I'll set this up and then I'll explain why we do this. One final thing, don't forget our unit conversion. Actually, let me do this. Let me put 1728. And then just to make it a bit neater, I'm going to scooch this over just a tad. Okay. Now, the reason we set it up this way is what we'd like to do is just integrate a single function. But we can't do that because we have two functions for our virtual diagram. So what we have to do is we have to break that up, and we have to integrate from 0 to 10, from 10 to 30. Now, we can use the same capital N, the real moment function, because it's valid for both ranges. What can get a little quirky is what happens when you have, different ranges for different functions. If you have like an M1 that works from 0 to let's game this like a simple example out. So if you have an M1 from 0 to 10, an M2 from 10 to 20, and an M3 from 10 to 30. Let's say this is probably not very realistic, but let's just actually, you know what? This actually probably could be realistic. Let me game this out. So let's say you had 3 little moment functions. But let's say you had 2 big M moment functions. Let's say this was 0 to 15, and this was 15 to 30. Like let's say this was what you had. Well, you'd have to split this up into a series of integrals. You'd have one from 0 to 10. You'd have another from 10 to 15. You'd have another from 15 to 20, and then another from 20 to 30. Because what you'd have to do is you'd have to say, okay, following my little m's, this is going to be M1, M2. This one's also going to be M2. This one's going to be M3. This one's going to be big M1, big M1, big M2, big M2. And if you notice, each integral is different. And so you'd have 4 different integrals that you would then need to sum up and then multiply by whatever unit conversion. So one thing I'll mention is that sometimes it's kind of nice to do this in a table format, that if you can set them all up and then integrate them one by one, sometimes organizing it in a table kind of helps. But this is a little bit outside the scope of this problem, so I did just want to throw this out here as an example. Let me erase this. I'm making all sorts of a mess. Okay. Now, from here on out, the problem becomes just a math problem, just a calculus problem. I can factor out the EI from both of these, and then we integrate from 0 to 10, and then I just plug and chug. So this is 2/3 times x, and this is 18x minus 0.6x squared, plus the integral from 10 to 30, And this is 10 minus a third of x squared. Oh, here I am forgetting my dx's. Plus dx. Okay. Now, here's the integrals that we have to evaluate. You can do this however you want. This is, you're not bound under any particular way of doing it. But sometimes what I do is when these things start to get kind of long is I will say, look, this is a lot. Let's break it up into smaller pieces. So we'll call this I1, call this I2. All right, so maybe I'll rewrite that a little neater. I1, I2. Okay, so let's do I1. Integral of 0 to 10 dx. Now, first off, before I start checking this out, you do realize, and I really want this to be clear, your Casio will just do this for you. So if you're lazy, just lazy, that's even kind of a harsh term. I would probably just plug this into a calculator. I find that to be an easier way to do it. But if you're one that wants to chug it out, that's fine. The key issue here, and this is going to be particularly true with I2, is that you do your multiplication correctly. Because for I2, we're going to have to FOIL. We aren't going to have to here, but let's just make sure that we're, chugging that out. Okay, 2/3 times 18, that's 12. So x squared minus 2/3 times 0.6 is 0.4 x to the third. I think we can do some integration now. 12 times x squared, x cubed over 3. There we go, 0 and 10. Make that a little smaller. And so plug in the top number minus plug in the bottom number. The bottom number is going to give you 0. And so that is there we go. All right, I2. I2. See if I can. All right, so this is foiling, okay? So first outside, so 180x minus 6x squared. Inside last, minus 6x squared plus 0.2 x cubed. All right, or all right, let me check and make sure that's right, because I'm doing this on the fly, and I would like to verify that I don't have any hiccups. 0.2x cubed minus 12x squared plus 180x. There we go. All right. So now we integrate. So 180x, x squared over 2, 90x squared minus x squared over 3, 4x to the third, and plus, okay, this is 0. There we go. And so minus all right. Let's do some figuring. 90. All right. I'm getting 5,500. All right. And one thing to keep in mind, you can always just use your Casio. So if I scroll up a bit, let's say to this first integral. All right, so integrate to, actually let's delete that. 2 times alpha x over 3 times 18 times x minus 0.6 times alpha x squared 0, 10, 3,000. And so you can see we got the exact same expression that we did before. And I can, if I wanted to, just reuse this. 10 minus, go in, call that 1. $10, 30. And so you can do it, with your calculator or by hand, whichever you prefer. You'll get the same answer. So if I go back here, go back to this. So, ultimately we're trying to determine the deflection at B, which equals all of this. So 1728 over EI. Right? So it ultimately boils down to just one fraction, 1728, 11,000, 4,000, 6,000. positive 0.792, or our conversion factor got us to inches, and then the positive value indicated we assumed a downward deflection. And we were correct. And that's it. So again, I think that the hard part is really like right here. That's the hard part. If you can determine this, a clear description for your real functions and your virtual functions, and then ultimately employ the principle of virtual work in order to split that up into your appropriate integrals, everything else is just plug and chug. So I think you'll find this is fairly straightforward. With that, I'm going to stop the recording. I'll post this to the playlist right after this processes, and so hopefully that'll give you something to help you with in regards to your homework. So that's all I have.